Uh,
Welcome, welcome everyone to the 111th meeting of Reactions in Group Theory and Categories. Today our speaker is Alexander Vishik from the University of Nottingham, and he will be talking to us about the Balmer spectrum of Voevodsky motifs.
so, first of all, I would like to thank the organizers for inviting me to give a talk at this seminar. So I will be talking about Balmer spectrum of Voevodsky motif. Voevodsky motif. Motifs is some linearization of the category of algebraic variety. And the respective motivic category was constructed by Voevodsky. It is called the Voevodsky motivic category. You know the DMK. Voevodsky motifs of a field. Category of Voevodsky category of motifs. Category of motifs. Motifs. The compact part of it is called the category of geometric motifs. Compact part. Both are tensor triangulated categories. These are tensor triangulated categories. And we have a motivic function from the category of smooth varieties to geometric motifs. Motivic function, smooth varieties of A to D, DMGM. Motivic function, which assigns to a variety its motive. And the motive of a variety carries some sort of homological information on the variety X, on algebraic variety. It's homological. Info on X. The category is tensor triangulated. In particular, it is additive and triangulated, and the direct sum and tensor product operations can be interpreted in terms of variety. So when you take the direct sum of the two motives of varieties, it's just the motive of disjoint union, the motive of disjoint union, X union with Y, and the tensor product of two motives is nothing else but a motive of Cartesian product of variety. Motive of X times Y. Right. Now we also have a topological realization functor, which permits to assign some topological invariants to algebraic varieties, and in particular topological invariants to motives. So topological realization functor. On motives, it will be a functor from DMK, from the Voevodsky category of motives, to the category of motives in topology, which is nothing else but derived category of abelian groups. It's topological motivic category. So this way we get some information about varieties, topological information about varieties and motives in general. Information, varieties, and motives. But unfortunately, this functor is far from being conservative. Being conservative. And the reason for this is that the respective map of Balmer spectra is not surgically from closed points. So the reason is that the map of Balmer spectra. PMK, it's contravariant, so it goes the other way. Let's put it GM here, and here dB of finitely generated abelian groups. And this is nothing else but the Zariski spectrum of Z. And so this map on Balmer spectra is not surjective on closed points. On closed point, which is a necessary and sufficient condition by the result of Balmer. So the task is to produce more closed points of the Balmer spectrum of the Voevodsky category. We need to construct more closed points of the Balmer spectrum of the Voevodsky category of geometric motifs. And some of such points are produced with the help of isotropic realisations. The isotropic realisations. The idea of isotropic realization is based on the notion of p-anisotropic varieties. So first of all, these points are analogs of topological points of characteristic P. We are talking about points of finite characteristics. So you need to choose certain prime P, and this prime will appear everywhere. So in particular, in the definition of a p-anisotropic variety. So we choose P prime, and then X is some variety, some field K. Then X is P anisotropic, if degrees of all closed points are divisible by P. Degrees of all closed points. That's divisible by P. And as soon as we have the notion of anisotropic variety, we can introduce isotropic motivic category. Definition isotropic motivic category. So I denoted dm k over k with fp coefficients. And this is nothing else but the Verdier localization of the global Voevodsky category of geometric motifs, of all motifs with respect to the localizing subcategory generated by motifs of p anisotropic variety. It's a Verdier localization of the global category dm k. We better take finite coefficients, although it is not important for what will follow, but let's do it with finite coefficients. So it's a Verdier localization of this category, global category, with respect to the localizing subcategory, generated by motifs of p anisotropic varieties. So in other words, we just kill the motifs of p anisotropic varieties. The idea that you may mod out anisotropic varieties belongs to Tom Bachmann, who used it in the study of the Picard group of the Voevodsky category, and he used for the subcategory. He used it for the subcategory generated by quadrant. And then you can get some results about Picard. So this is the definition. unfortunately, to get some category which would have the needed properties, you need to choose K carefully. It's the next observation. You can't just do it over an arbitrary field. So need to choose K carefully. K carefully. And this is related to the following example, right? So this is apparent from the following example. So take K to be algebraically closed. K is algebraically closed. Well, then you may observe that the isotropic motivic category is the same as the global category because there are no anisotropic varieties, right? Because all varieties have rational points. Okay. If K is algebraically closed. It's the same as a global category. As all varieties are isotropic. They all have rational points. Hence, no simplification. Right? So nothing interesting have happened. Right. No, certainly it's not something we need, right? Because this category will not have the property. But fortunately, there is a good supply of proper fields. And these fields are called flexible. Definition. Okay, it's flexible. If it is a purely transcendental extension of an infinite transcendence degree of some other field. You have some other field K0 to which you adjoin infinitely many parameters, algebraically independent parameters. And moreover, if you there's an arbitrary one, you can always pass to the flexible field by adjoining such parameters. And this is called the flexible closure. A tilde is just a flexible field obtained from a given one by adjoining infinitely many parameters. This is called flexible closure. Notice this passage from the ground field to the flexible closure is conservative on motives. So you don't lose any information. No, and as soon as we have this, we can introduce isotropic realization. Well, we can introduce isotropic realizations. We suppose P is prime, and E over K is some field extension. The extension. Then we can consider the following function, which I denote psi P E over K. And it is the following composition. So you start with the Voevodsky category of motives over K, and then you pass via the usual functoriality on motives to the Voevodsky category of a flexible closure of E. No, first you pass to E and then to flexible closure of it. And after that, you project the isotropic motivic category corresponding to this flexible closure. And now we reside in the isotropic motivic category of a flexible field. And such categories are nice. So they have the needed properties. So this is what I call an isotropic realization. So it is parametrized by prime number P and a choice of a field extension E over P. So it appears that, for example, for the purposes of construction of a family of conservative functors, conservative family functors, you don't need to use all the extensions because some extensions will give the same kernel, produce the same kernel, and this will happen if and only if extensions are what is called equivalent, p-equivalent, equivalent in the sense of the prime P. Right, so let me introduce this equivalence relation on the extensions. Right, and it comes from certain partial P order. We have a partial P order, on the set of extensions. The order is the following. So suppose you have two extensions, E over K and F over K, then we say that E over K is greater or equal than F over K, in the sense of P, if you choose some smooth model of F. Now assume first that F is finitely generated, and P large is a smooth model of F. Then this then this smooth model restricted to P should be P isotropic. Is P isotropic. Isotropic where F is equal to K of P. Can you hear me well? Still?
Yeah.
Yes.
Yes,
Thank you.
yes.
Right. So this is how you define it in the case when F is finitely generated. And then if F is arbitrary, then you say that you have an equality if E is greater or equal than every finitely generated subfield of F. This is how you define it in general. Right. So it's easily extendable to an arbitrary case. And then we say that two extensions are equivalent if and only if they are equal in the sense of this partial order. Two extensions are equivalent if you have inequalities in both directions. Well, we can introduce the needed ideal. So we introduce the order. So now we can introduce the point. The point of the Balmer spectrum. It's the ideal given by this realization, the kernel of isotropic realization. By definition, it's the kernel of this isotropic realization restricted to the compact part. Restricted to the compact part. And we have the following result. The main result, which describes the situation, it's the following theorem. So first of all, it's a prime ideal. So it's indeed a point of the Balmer spectrum. P over K is prime. Okay. And then also we can say when two such points will be equal. They will be equal if and only if the respective primes are the same and field extensions are equivalent. A, P, E over K will give you the same point as Q, F. Okay, if and only if primes are the same, because a prime is nothing else but a characteristic of a point, because it is an invariant, and also extensions E over K are equivalent, and F over K are equivalent in the sense of this prime. Right. So this gives you a way to construct many points. Many points. We get a lot new points. Isotropic points. Of the Balmer spectrum. And so the following example gives you an idea how many. Really a lot. So example, so consider K to be the field of real numbers. No, then we have there are 2 to the power continuum different points of characteristic 2. Isotropic points characteristic 2. And in particular, it tells you something about the cardinality of the Balmer spectrum as a whole. Particular cardinality of the Balmer spectrum, space D M GM R is the same as the cardinality of the set of all subsets of the category. Sets of the category. So we get really a lot of points. Right, now I'm going to switch to prime 2. Right, so what follows will concern prime 2 only, because in this case we understand the situation somewhat better, because there are some additional statements which are not known for what follows. Here, situation is understood better. It was based on the following geometric fact, which also should be true for arbitrary prime, but it is not proven. Based on the following geometric fact. Geometric result. It's the following theorem. Assume that characteristic is not true. No, otherwise all the constructions are in characteristic 0, but this statement, because it is geometric, I formulated in this generality. And suppose X is any projective variety. Any projective variety over K. Then just maybe close. It exists. A purely transcendental extension. K of A over K, and the pure symbol. Symbol alpha in Milnor K theory over this extension mod 2, such that for arbitrary extension L, okay, the following conditions are equivalent. So variety X restricted to L is to isotropic, if and only if alpha restricted. No, you can't restrict it to L, but you can restrict it to L of A. If alpha restricted to L of A is 0. We notice that if alpha would be defined over the ground field K, then this would be just the definition of a norm variety for alpha. X would be a norm variety for alpha. What is claimed here is that an arbitrary projective variety can be realized as a norm variety, but just not norm variety for a pure symbol. You think the pure symbol doesn't have to be defined over the ground field. It may be defined over some purely transcendental extension. Right, but otherwise it's the claim that any projective variety is a norm variety for an appropriate symbol. This is what it says. No, and it permits to see various useful things. For example, you can see that equivalence class of relations of extensions, is distinguished by the kernel on Milnor K-theory mod 2. So let me introduce some notation. So let me define as P of a kernel, a pure part of the kernel. And you pass from one field to some extension. Just pure part, kernel. Kernel, when you pass from Milnor K-theory of K modulo 2 to Milnor K-theory of E modulo 2. So, and then the corollary of this theorem is the following one. Suppose you have two extensions, E over K and F over K are some field extensions. Then we have the following. So we can interpret partial order on extensions and also equivalence on extensions in terms of pure symbols. Pure symbols over flexible closure. Namely, one extension E over K will be greater or equal than F over K in the sense of the prime form, if and only if the pure part of the kernel, the second extension, restricted to flexible closure, F tilde over K tilde, is a subset inside the kernel of the for the first extension. Again, restricted to the flexible. And from this, it formally follows that two extensions will be equivalent if and only if pure partial kernels are the same. This is equivalent to the fact that pure part of the kernel of F tilde over K tilde coincides with the pure part of the kernel over E tilde over K tilde. So if you know the kernel on Milnor K-theory mod 2, then you know the equivalence class of your extension. The only thing you need to do it not just over the ground field, but over the flexible closure. Compare them over flexible closure, then you see the equivalence classes. And this permits to see various things, in particular for prime ideals of Balmer spectrum. To study prime ideals of the Balmer spectrum, we need some test spaces. Distinguish ideals in DMG. And such spaces are related to Rost motives. So let me recall you what Rost motive is. So suppose you have some pure symbol mod 2. Pure symbol A1, A2, AN, pure symbol of degree n, in Milnor K-theory, n of Milnor K-theory, K modulo 2. So then to such a pure symbol you can assign a norm variety for this pure symbol, which is a Pfister quadric. Which is a quadric corresponding to a quadratic form of dimension 2 to the n. So it's the form denoted this way: A1, A2, etc. An with double brackets, which is the product of n binary forms. N binary forms AI. I, where the binary form A is given by norm in the quadratic extension k square root of A. So it is a quadratic form x square minus a y square, two-dimensional form. So as a result, the Pfister form has dimension 2 to the n. And it was observed by Marcus Rost that the motive of a Pfister quadric can be divided by the motive of a projective space of half the dimension. Motive Pfister quadric alpha can be divided by a motive of a large projective space, and the quotient is denoted M alpha. Denoted M alpha, and is called the Rost motive. No, because the motive of a projective space is a sum of Tate motives. What is said here is just that the motive of a Pfister quadric is a sum of shifted copies of Rost motive. M alpha is a Rost motive. So what do we know about this Rost motive? So over algebraic closure, it becomes just the sum of two Tates. It's just the sum of two Tates. Tate motive plus Tate motive shifted by this 2 to the n minus 1 dimension of projective space, basically. N minus 2. And moreover, not only you have this decomposition of K bar, but some of these maps to and from Rost motive to the respective Tate motives are defined, half of the maps are defined already over the base field. So namely, we have a projection from M alpha to T, and then a map to M alpha from the large to Tate motive. I just denoted D to D, where D, of course, is equal to this number, right? D is equal to 2 to the n minus 1 minus 1. And this composition is 0, and then you can produce the upper half of the respective octahedron in the triangulated category, so you will get this sort of diagram. Where you have shift, there you have shift, so here you have shift, and 2 points are distinct. So you can cut these two cells from M alpha, and after that you get what is called a reduced Rost motive. Reduced Rost motive. Reduced Rost motive. No, in some sense, this picture is symmetric. It corresponds to the semi-orthogonal decomposition of the Voevodsky category corresponding to two complementary projects, which are the motives of the respective check simplicial scheme and reduced check simplicial scheme of the Pfister quadrant. And in this picture, alpha carries exactly the same information as all the objects which appear, as Pfister quadric, as M alpha, and also as the reduced Rost. Alpha carries the same information as U alpha, and also as M alpha, and also as the reduced Rost motive M alpha tilde. But M alpha tilde is the most economical multidimension. So all algebraic closure disappears completely. Right? It is a form of nothing. And also the ground field, it has only finitely many diagonals in motivic homology. And this means that in the homotopy structure, it has only finitely many homology objects. And the exact number of such non-trivial diagonals is 2 to the n minus 1. So M alpha tilde is 2 to the n minus 1 non-trivial homology objects in the homotopy structure. Homology objects, of course, are elements of the heart of the homotopy structure. And the heart of the homotopy structure consists of cycle models of Rost. Homotopy structure. All isomorphic. The principal ideal in Milnor K-theory mod 2. Alpha times K M star up to shift. Up to shift. Isomorphic up to shift. Where this Milnor K-theory mod 2 is the Rost cycle model, which is the Milnor K-theory mod 2, Milnor K-theory divided by 2. So consider it as a Rost cycle model. Cycle model, which is in other words, an object of the heart of the homotopy structure. Right. It is useful to also recall the case of n equals 0, which is not formally covered by the above situation. N equals 0. In this case, we also have a non-trivial symbol which doesn't have any entries, which is the unit of the Milnor K-theory. And in this case, of course, the M alpha tilde is nothing else but this unit of the homotopy structure of the category with F2 coefficients. Milnor K-theory mod 2. And this is nothing else but a con of tau. Con of tau. Right. So this is how you may interpret con of tau in the context of this reduced Rost motif. It's an example of a reduced Rost motif. Right. Now, notice that also in this case M alpha is 0. The Rost motif itself is 0. Worth mentioning. M alpha itself is 0. Now we can try to distinguish points, right, by looking at by using these objects, M alpha and M alpha tilde. Can try distinguish points. Balmer spectrum D M G M K by objects M alpha tilde for various symbols. So note in particular that the product of two such objects is 0. If you tensor them, M alpha and M alpha tilde, then you get 0. So in particular, any prime ideal contains one of them for every alpha. So you automatically get two subsets, the set of pure symbols. One is made of those alphas for which M alpha is in your ideal, and another for which M alpha tilde is in your ideal. And the union of two subsets will be the full thing, definitely, right? Because ideal is prime. Let's look at some examples. So the first case, suppose case flex. Then the isotropic ideal A to K over K is generated exactly by all M alpha. It's generated by all M alphas, all alpha, non-zero alpha. And the opposite case will be the case of the etale ideal. So A2 etale, etale ideal of characteristic Thor will be generated by the cone of Thor, right? By the cone of Thor. And this is the same as being generated by all M alpha M alpha tilde for all alpha. Because if you have some M alpha tilde is a new ideal for some alpha, then you can always multiply this alpha by any other symbol, and the result, the respective M beta tilde will be still in the ideal. So in one case we have only M alphas, in the other case we have only M alpha tilde. So this is a prototype how it should work, but of course in reality we need to generalize it a little bit to make it work for arbitrary fields and in general. Right. So we need to generalize it. And for this, let me introduce the set of pure symbols inside Milnor K-theory mod 2. Milnor K-theory mod 2 considered as a Rost cycle model. It's a set consisting of the following pairs. So first of all, you take some finitely generated extension E over K, and then some non-zero pure symbol alpha over this extension. E over K, finitely generated extension, and then alpha is non-zero pure symbol in Milnor K-theory mod 2. Pure symbol. And it is naturally a subset inside the unit of the homotopity structure with F2 coefficients. So now, if you have such a pair, E comma alpha, then we can produce certain compact object of the original category. And we do it as follows. We consider certain open neighborhood of the spectrum of E in some smooth model of E. Let Y be open neighborhood of spectrum of E in where M alpha tilde is defined. So it will be defined not just in a generic point, but a little bit around. And we just take this open subvariety where it is defined. So we get an object which I called M alpha over Y tilde. No, we substitute the generic point of Y by a bit larger variety. And in particular, it's a variety of finite, Y is a variety of finite type over the base field. So as a result, you get a certain geometric motive over the ground field. Geometric motive with F2 coefficients. Right. Now suppose now we have some prime ideal in the Voevodsky category. Let A be a point of the Balmer spectrum of geometric motives. EM, GM. So then we can define a couple of invariants. So first of all, we can introduce the set G of A. It's a subset of pure. Both will be subsets of pure, and G of A is the set of those pairs E comma alpha, such that the object M alpha over Y tilde orthogonal complement is contained in A. And the second subset will be H of A, which consists of those pairs E alpha, such that the object itself is contained in A. So then, of course, because the product of two such things is 0 and A is prime, we get that G of A union with H of A is the whole pure, right? The whole set of pure symbols. So now let's look what happens when our point is isotropic. Let's look at the isotropic case. Isotropic case. Right. We have the following result. In this case, the subsets will be disjoint. Right. So G of the isotropic point F, F over K, intersection with H of A F over K is empty. The first statement. No, and then you can describe both G and H. No, since they're complementary to each other, let me describe H. No, so let extension E, which participates in the pair, will be the generic point of some variety P. So then this H of E to F over K contains the pair E comma alpha if and only if either alpha vanishes over F, either alpha vanishes over F of P, of course, because it was defined over K of P. Or the second case is that P restricted to F is anisotropic. Right? Or P is anisotropic. So we have complete description of the respective invariants for the isotropic case. You can say, in particular, you can distinguish them, right, among themselves. And also this way, one can compute, or describe the isotropic ideal. The isotropic ideal A to F over K is just the union of all pairs E alpha from G of A to F over K of the orthogonal complements to these objects. M alpha over Y tilde orthogonal. Right. So in particular, for the isotropic case, the respective ideal contains certain things which all ideals with given characteristic G do. And this shows in particular that these points are closed. Corollary of that is isotropic points are closed. In particular, they are not specializations of each other. Isotropic points are closed. Right. So we get two invariants of a prime ideal in the Voevodsky category of geometric motifs. One is H of A, right? And this is a subset of pure, which in turn lives inside Milnor K-theory Rost cycle model. And this subset is a weak, what I call a weak Rost cycle submodel. Cycle submodel. Weak means that it is subject to 3 operations only. So in general, if you remember the definition of a Rost cycle model, it's a certain functor which assigns to every finitely generated extension of the ground field, it assigns certain graded abelian group on which you have 4 operations. So first operation is restriction. When you have embedding of one field into the other, you have functoriality from smaller field to larger field. Then you may multiply. You may multiply by multiplicative elements, so which gives you the action of Milnor theory on your graded abelian group. And then the third operation is residue, which is related to some discrete valuation ring. And finally, you have transfers. So the weak Rost cycle model has 3 of them, aside from transfers. No transfers. But the good thing is that the other 3 operations, they preserve their purity. So they map pure symbols to pure symbols, right? In contrast to transfers, which in general don't do it. Right. So we get certain weak Rost cycle submodel. Another feature of a weak Rost cycle submodel is that there is no addition, right? It's only a set. It's not a group, right? And the other G of A will be a complement. Is a complement and pure to some other weak Rost cycle submodel. Is a complement. Pure weak Rost cycle submodel. So if we denote H of A to be this Rost cycle submodel J, and G of A to be pure without submodel I, then we have this situation. So I must be embedded into J, embedded into pure. I embedded to J, embedded into pure. The boundary case corresponds to the situation when I is equal to J. So we have the boundary case. This I equal to J. And all isotropic points are such. Finally, let me just give you an example of a point which is not such. It's an etale point. Example, etale point. So in this case, J is everything. It's the whole P1. But I is smaller. I consists only on the kernel of K bar over K. No, of course, consider it as a submodel of the Rost cycle model. It consists of pure symbols, non-zero pure symbols, which vanish over algebraic closure of K, of the ground field K. Notice that these symbols are not defined in general over the base field. They are defined over some extension. So this is why they may not vanish. There are symbols which will not vanish. But if K itself is algebraically closed, for example, then I will be just empty. Right. So there is maybe a special case, K equal to K bar, then I is empty. An empty set. So J is everything and I is empty. Right. No, and the natural questions are which pairs of I and J are possible. And for example, in the boundary case, does this Rost cycle model, weak Rost cycle model I, or equal to J, does it determine the ideal uniquely? Right. So these are the next natural questions. Right. Now let me stop here.
Thank you, Sasha. Let's all unmute ourselves and give the speaker a round of applause.
Maybe I will use my my camera.
Yeah. If you have any questions, please ask them.
I have a very simple and stupid question, standard one. What are your future plans?
Well, no, first of all, to
And
study.
hopes, maybe.
No,
Your
to
plans and
study
hopes.
this possible combinations of I and J, and no, in the end to try to describe the spectrum completely, of course. But no, so far I would like to answer various questions about these invariants which appear, but there are quite a few.
Thank you, Mikhail. Any other questions?
So you made this comment in the past, and I'm just repeating what you said, but you didn't say it today. So you said that the points corresponding to these pairs, those field extensions, they would be the same point if the E and the F were p-equivalent, but
Right.
you have this partial order.
Yes, yeah.
And but on the close points, what does it mean to have? What is the meaning of this partial? Have you solved that?
Yes, no, of course, this meaning is nothing else but the inclusion of one of G of A into the.
Right. So in terms of the pairs, you can say that. So the pairs are disjoint in that case, but you're just saying.
No, they are all closed, certainly, right? So they are not specializations of each other. In terms, right? So what? Yeah. So let me, maybe remove.
So you're saying you can translate it in terms of invariant IJ,
Right.
but intrinsically in terms of, if we think, like in the spectrum of a commutative ring, we are talking about different close points, but you can, in some cases, compare those close points, which is not a comparison by inclusion, but do you have a kind of a geometric meaning of this inequality in that case?
No, there is some meaning in terms of these invariants, G and H, right? In terms of,
Right.
so for example, equivalent. So first of all, the order, as you can see, it is equivalent to the fact that there is an embedding. Yeah, here it is. There is an embedding on pure part of the kernel, right? One kernel is contained in the other. And also, I think there is a similar, there should be similar embedding on for which P it will be anisotropic and isotropic. Right. So I think it is just if I'm not mistaken, I think it is just the embedding of the respective either G or H, one of them. Yeah. So they're embedded into each other.
Right.
So
that kind of gives a translation of the inequality in terms of the subsets of the pure that you
yes, yeah.
that you get.
Yes.
But it is not yet a kind of intrinsical characterization in terms of the close points in the spectrum, or I don't know, some residue field, some geometric invariant that you could associate to those points.
Yes. No. So we have these invariants related to test spaces, right? So we can interpret it in terms of relation to test spaces, but no, in some sense it's also characterization, but of course it's a little bit artificial because we.
And those test spaces, how much are they? How geometric are they? I mean, are they the spectrum, the Zariski spectrum of something classical? Is there a chance that?
No, but it's no. First of all, they are geometric, right? So they are compact. These are compact objects. Compact objects. No, it's basically you take the reduced Rost motif and you extend it a little bit beyond the generic point, right? It is defined originally in the generic point of some variety, and then you extend it to some small neighborhood of this generic point. Right. No, so you can see that it is obtained from three motifs of three varieties, right? So first of all, you have Pfister quadric over generic point, which is defined. No, this quadric fibration is defined not just in the generic point, but a little bit around, right? Clearly, and also projector is defined a little bit around the generic point, and you take the direct sum and inside this Pfister quadric over some neighborhood of the generic point of quadric fibration. And then you have two copies of y and also y shifted mapped to and from this Rost motif. So it is obtained from three motifs of varieties, if you want, or direct summons in the motifs of varieties. It's not very complicated, right?
I'm not sure. Yeah, maybe my question was not clear, but we'll have opportunities to talk about that.
Okay. Thank you, Paul. Any other questions? Anybody? Well, if we don't have any more questions, let's thank the speaker once again.
Thank you, session.
Thank
Thank you.
Thank you.
Yeah. Thank you. Thank you all for coming.